All right. Hi, Math 2504. Here is a little video just giving you a bit more information for project two, just a bit of a guided reading. Like a lot of our assessment, there's a lot of information. So here it is. So, of course, it's do here, work in pairs, fine. Submission format is just like project one, pretty much. It's only that this time you don't have a GitHub repo that you copy. 10 points are for following instructions. There's always 10 points for the perspective seminar and 80 points for the projects. These 80 points for the projects, 60 of them are for correctness of the results. So as you see below, I'll describe this in a few minutes. You need to create some plots. I think you effectively need to create like 15 plots because there are 3 plot types and 5 scenarios. So 3 times 5 is 15. So each plot type will give you 20 points. And then you get 20 points for style, design, code organization, neatness, and stability of the output, etc. In general, points will be deducted for sloppy coding and stuff like that. All right, setting up the GitHub repo just like before, but what you need that you didn't have before is to have some basic running instructions on how to run this. So in the first project, Polynomial, we gave you a bit of a README. Now you should have some basic running instructions which say, hey, to run my code, just download and do this and this and this. Okay, it should be simple. Perspective seminar. I hope you enjoy Anna's seminar. It's related to the project in a general sense. So here's a main project task. So what you're doing is a discrete event simulation of a queuing network. Okay. You can think of this network as potentially modeling something like an amusement park, like this Dream World. I don't know. I've never been there. I've been in other amusement parks, Disney World. But anyway, no, I haven't been to Disney World. Well, that's irrelevant, actually. Okay, so anyway, it can model an amusement park. Okay. And in the amusement park, you've got multiple servers. Okay, multiple rides and individuals, customers, jobs, whatever we call them, people are moving between the servers. So let's get the notation right. So we've got these servers are, well, they're stations, okay? A station has a server and it has a waiting buffer. So L is the number of stations. And their jobs are customers or individuals or packets or whatever traversing through these stations. And you can have a unique number for the jobs. Okay, job 1, job 2, job 3. You're actually supposed to create this in 2 modes. In one mode, you're tracking each individual job. In another mode, you're just tracking the cumulative number of jobs in each station. You potentially can do, you need at least, you need the mode where you track each job to look at the time it took a job to traverse. So where can a job be? So a job can be out of the system. It just hasn't arrived. A job can be in the buffer of one of the stations queuing, standing in line. A job, yeah, again, is a customer, right? A job can be served, so it's actually being served by a server. Now in Dream World or whatever, many jobs can be served in parallel by one server, right? You seldom have a ride that just takes a single person. But here the server just serves one job at a time. Okay. Or the job can be like in the system moving between the stations, the servers, or it can leave. This is a continuous time system. Okay, but you're going to do a discrete event simulation. And jobs arrive according to a random process, which is just independent sequence of inter-arrival times that are gamma distributed. And then they traverse between the stations. So let's see. Each station actually has a service rate. So that number mu means how fast the station can serve. 1 on mu, 1 divided by mu is the mean service duration for a station. Okay. And each station has a buffer capacity. And then the capacity can be like 5 or 10 or 20. So how many jobs can wait in the buffer? and it can also be infinity. Okay. When a job arrives to a station, if that server is free, so that means there's also no jobs in the buffer, then it immediately begins service. If the server is busy and there's a waiting room, so typically unless k is 0, there's going to be a waiting room, then the job enters a queue. Okay, just like the queuing examples you're going to have in the lectures. However, if the buffer is full, so if there are exactly k jobs in that buffer, then the job says, oh, I can't be here. So it's like an amusement park going and seeing everybody standing in line, say, oh, the line is full, I cannot be here. So it goes someplace else, according to an overflow rule, which we describe below. Okay, duration of events follow independent random variables. So the duration of time between external events have a mean of 1 on lambda. So lambda is the arrival rate. So you get lambda arrivals per unit time. The durations of service times are 1 on mu I. Okay. And the duration of time moving between station when overflowing, so when you're orbiting between the stations, when job orbit, is 1 on eta. So eta is, you can think there's like this infinite capacity place, which is called the being between stations. And in that duration, each job individually moves at rate 1 on eta. And the duration of time moving between station after service is again 1 on eta. So when a job is inside the system, but it's not being served, then it has, independent of everything else, a duration of time until it goes to its next location, which is with mean 1 on eta. All these durations are gamma distributed. The practical is going to show you how to generate these things with a squared coefficient of variation of 3. So that should be clear from the practical this week. So the parameters for durations, you've got that one number lambda, you've got that one number eta, which is going to be fixed actually for everything, and you've got the sequence of mu's. Okay, these are always inverses of the means, they're rates. When a job completes service at a buffer, it either leaves the system or it moves to another buffer. So you just finished a ride, you can say, oh, I had enough of this, I'm going home, or no, you continue. So the choice of where you go is according to the probability Pij. Okay, so if you're at buffer I, you go to station J with probability Pij. And all this thing of that P has a non-negative entries, has a spectral radius less than 1, it just means that jobs eventually leave the system. And it also implies that these are actually probabilities in this matrix. So each row is a sub-probability distribution because each row, the sum of each row is at most 1. It can be a probability distribution. But if there's a possibility to leave, then that's 1 minus the sum of the elements of the row. Okay. So that's how you read the routing matrix P. I'll show you in examples below. Now, similarly, when a job arrives to a full buffer, it must overflow. And that goes according to a destination buffer. Again, your job arrives to buffer I, destination J, with probability Qij. Okay. And this is a probability of overflowing and leaving the system. And when an external arrival occurs, so arrivals occur according to this process with a rate with an inter-arrival mean of lambda, so that's a rate of lambda, then these arrivals go kind of for their first ride, for their first station, for their first server, according to the probability vector PE. So that's a vector of dimension L as well. Okay. So that's how it works. Now, there's kind of two main modes where you'd want to do this discrete event simulation, and you'd want to program for both modes. So in one mode, which you won't see explicitly in the lecture, each job is really an entity of the system. So then you really keep the identities of a job 1, job 2, job 3, and these identities just keep growing, and they're actually bits of information. So there's some type in your system, a job, and each job is going to be someplace. Okay, so you keep track of all jobs, and that actually allows you to know how long the job spends in the system, etc. The other way is that you only keep track of the number of jobs. So number in service, number in waiting buffer, and number in orbit. Okay. So that's, you've seen examples like that, or you will see in the lecture and the practical. But your simulation should support both modes. The first mode, only station statistics. Join the station statistics may be collected from a simulation run. The second, individual job trajectories can be collected. So you're given 5 different input parameter scenarios, and these are described in the code below. We'll look at them in a second. And each of these scenarios specifies a network structure via the matrix P and the Q and the vector P superscript E of where you get to, the service rates. And you'll always take the eta to be 4. So that means that the mean time between stations is 1 on 4. That's a quarter. Okay, and what you're going to do is you're going to vary lambda. And in each case, you'll do a simulation run for a long time horizon. Of course, you'll first debug and develop, and that's up to you and your partner to do it well. And then you'll run for a relatively long horizon. That's not so long, for 10 to the 7th time units, and collect some statistics. So you'll run that on a grid of lambda values. Okay, so what are you going to do? You're going to create 3 plots, and that's kind of your 20 points, 20 points, 20 points. So the total mean number of items in the system. I mean, you can guess that as you increase lambda, you bring more to the system, then the mean number of system in the system will grow. So that's the first thing. Okay, so even though this is a complicated system, all you're going to count is a total number of items in the system. Being in the system means being served in one of the stations. It means being in the buffer of one of the stations, or I mean, it's being between stations. Okay. And the second plot is going to be the proportion of jobs. So that's something between 0 and 1 that are in orbit, circulating between nodes, right? So you've got these jobs that are in orbit each time, where they have like a mean orbit time on 1 on eta, okay? And you can think what you're going to see is that when lambda gets high and high and high, then actually you have more and more and more jobs in orbit, especially if your buffers are kind of full, depending on which scenario it is. The third thing, and for this you need to do the first type of simulation. You can do, by the way, all of them with the first type of simulation, but the second type of simulation is faster. Okay, so with the first type of simulation, you'll do the third plot, and that's keeping the empirical distribution of the sojourn time of a job through the system. So how long does it take somebody to go through the system? That just means time from, missing a bracket here, we'll fix this. Okay, is varied as a function of lambda. So time from arrival until departure, that's sojourn time. So that's, each job has quite a complicated path, but that's a sojourn time. So collect the empirical distribution of that. Show a histogram or cumulative or empirical cumulative distribution function or some other similar plot. So in each of these cases, you'll do a long simulation path. One path is effective for this. I mean, for more serious simulation, of course, study, you do much more, but we just do one path. Okay, you'll assume that one path captures everything. That may actually not be the case if lambda is too high, but you'll just assume that's the case. Okay, and then you'll go over some grid of lambdas. You'll have to experiment on how you do that grid, and then you'll collect the numbers for the plots. We're still running these simulations in some batch. That should also all be described in your README file. Just run the simulation. It's going to run the simulations. You might have unit tests as well. That's up to you. Now, discrete event simulations sometimes become a bit more tedious to code if 2 things can happen in the same time. For example, a job can enter service and leave service, or 2 jobs leave service at the same time. Just assume that this doesn't happen, so you don't need to program for such cases. And you can, of course, use the code provided in the lecture and the tutorial and anywhere else, as long as you eventually own it. Now, here are the 5 scenarios. So what you have here is a struct which just specifies a scenario, all of the parameters of the scenario. You don't have to use the struct per se, but you can use it directly. This macro just comes from the parameters package, and it allows you to, it gives you a constructor that's kind of uses named arguments easily. You can look at the parameters.jl package here. Not a big deal. Okay. So, for example, scenario 1 has 3 stations. Gamma shape is always going to be 3 in all of them. Lambda is not specified because you're going to vary it. Eta is always going to be 4. The mu vector, all stations are homogeneous in terms of the fact that their service rate is 1. In this routing matrix, look, you go from the first job, from the first station with probability 1, you go to the second station. From the second station, you go to the third station. And from the third station, this is all zeros, you go with 1 minus the sum of the probability. So with probability 1, you leave. So this is a tandem system. And Q is all zeros. So there are no overflows, and you arrive to the first station. So this is actually not so different from the thing that you have in the practical. Only that K is has buffer sizes are 5. Your second example is, I think, very similar. All again, 3 stations, all the same. Only that with probability half, you now from the third station you go back. So when a job finishes service in the third station with probability 0.5, it goes back to the first station. Okay, so it says, oh, I finished. I did ride 1, I did ride 2, I did ride 3. Oh, I'm going to the first one. Or no, I had enough, I'm leaving home. Probability 0.5. Okay. Yeah, and again, no overflows, and the rest is the same. Okay, so scenario 1 and 2 are kind of similar. When it does this with probability 0.5, if it decides to go there, then it's going to be for a duration of 1 on eta in the waiting room. It's kind of walking, right? Or maybe it's getting an ice cream or cotton candy, something like that. Okay, so this third scenario is still only with 3 stations. Only now, oops, now I'm confused. Scenario 1, scenario 2, scenario 3. What's different? 1, 1, 0.5. I think I messed this up. So I will replace this third scenario with something more meaningful. It wasn't supposed to be exactly like the second scenario. Okay, so that's the third scenario, fourth. Yeah, I'm not sure. So yeah. Oh no, sorry. Of course, sorry. I'm not going to do this video again. It's going to stay on YouTube like this. Come on. So in the second scenario, you don't have overflows. And in the third scenario, you suddenly have overflows. Okay, so if the second buffer is full, then with probability is if the first buffer is full when the job arrives, then, and that's going to be more and more probable when lambda is bigger, then with probability 0.5, you go to the second buffer. You immediately kind of skip. And here, if the second buffer is full, then with probability 0.5, you go to the third buffer. And similarly, the third buffer, if it's full, you probability 0.5, you go to the first buffer. So here, there are suddenly overflows in this scenario 3. Okay, scenario 4, we've got 5 jobs. And the mu vector is slightly different. So now it's not a uniform mu vector. You've got 5, 4, 3, 2, 1. Okay. Yeah, and let's see that we got this correct. When we look at scenario 4, mu vector, yeah, 4, 5, 4, 3, 2, 1. Okay, so kind of the first, that means that the first server or the first station is fastest. 5 is very efficient. Okay, it's very quick service, the mean 1 on 5, whereas the last station is slower. The routing matrix is a bit more complicated here. Okay, so for example, from the 5th one, you go uniformly to all the others. Okay, but from the fourth one, for example, you exit the system. Okay, so you can only exit the system from the fourth one in this case. And here's the overflow matrix as well. Okay, now this -1 here is one way to encode infinity. We could have had these as floats and then you just put infinity, but with integers you don't have infinity. So look, we said you have a vector of ints where -1 means infinity. Okay, so infinity means there's no upper bound on the capacity of the buffer. So these are 2 infinite buffers and these are 3 finite buffers. This fifth scenario is a bit bigger. It doesn't look big in code, but it's big in the number of servers. And all servers have the same service rate. There's actually no routing. No routing, so P is zeros. So when you finish service, you leave. However, the queue is a diagonal matrix with some ones in the off. Well, just look at it, just see what this matrix looks like, but it's basically has some ones and some more ones. Okay, so basically, if a buffer is full, then you skip 2, except for the last one. So you can look at what this queue looks like, just run it and print it out, and that's what the queue matrix is. And this PE means that you arrive to, in the previous one, you arrived kind of in according to some different probabilities to the first job, first server, second server, last server. Here you arrive to the first server, certainly not to the other 19. Okay, so that's the scenarios. And I hope that this gives you enough information to get going. This plus the lecture and the practical should, and plus a lot of fierce discussions with Piazza, consultation hours, most importantly with your partner, should help you get going on this. Okay, take care. Bye.